All right, so these are our kind of introduction to kinematics and motion graph notes. This first part of the year in physics, it's all about understanding the science of motion. That's what kinematics is. It's the science of motion. Because physics is all about things moving, so we have to start with this kind of basis of how we talk about things that move. How can we analyze it? What can we measure? And how do we talk about those things that we measure? So let's get started with some of our big vocab terms. And the first one is going to be velocity. Whenever we talk about velocity in terms of like mathematic equations, we're always going to use a lowercase v to represent it. And we've come up with this definition for velocity from the couple of labs we've done so far, that velocity is just an object's change in position over change in time. Okay? And what we can do is we can kind of shorten that. We can take that phrase there and shorten it into more of a mathematic equation here and say, we're going to use this Greek letter. It's called delta, just means the change in. So the change in position, the variable for position is x, over the change in time. So there is kind of our starting equation. It is one way you can calculate the velocity of an object, is you can take the change in position and divide it by the change in time. The only issue being that we can only use this equation if an object has constant velocity. If it doesn't have constant velocity, then we aren't going to get accurate numbers using this equation. So you can sometimes use it in this class. We're not going to very often, just because things that have constant velocity, kind of boring in terms of physics. So I'm going to write that down. This only works if you have constant velocity. Right? Okay, let's also talk a little bit about units for a second. So if position is measured in units of meters, time is measured in units of seconds, then what are the units for velocity going to be? Well, it's just going to be, oh, here, we can do this one. It's just going to be meters per second. All right. Moving up, we have acceleration up next. Acceleration, we are going to symbolize it mathematically in equations and stuff as a lowercase a. And it kind of follows the same trend. From our definition in velocity, where acceleration is the change in velocity over the change in time. Again, we can shorten that. We can say delta v, so change in velocity over change in time. Now to figure out the units, we're just going to do the same thing as last time. Velocity is in meters per second, time is in seconds, so it's going to be meters per second squared. All right. Now this is an equation that we're more likely to use in this class. It requires the object to have constant acceleration, which will be most of the objects in this class. So it will come up more often and kind of be a more usable equation there. All right, now let's focus in on this variable right there. Delta x, change of position. In physics, it's really important. We actually have a separate term for what it is. We call it the displacement of an object. And the displacement of an object is just the difference in an object's final and initial positions. The difference, you know what, let's change this real quick. Rather than difference in, I'm going to say the difference between. The difference between an object's final position and its initial position. So a lot of times I will take sentences like that and turn them into more mathematic equations. I'm more a mathematically brained person, so it's helpful for me to see it in terms of an equation. And I would write it out like this. If I wanted to find the object's displacement, its change in position, I would take its final position and I would subtract its initial position. So displacement is interesting, and it's very similar to the concept of distance, but they have some key differences that are important to discuss. Take this as an example here. So let's say I started at this white dot here, and then I followed this green trail all the way around the board. Maybe this is like a bird's eye view of a field. So I followed this green trail all around the field, and I end up here at the end. If I were to measure the distance, well, the distance that I've covered is kind of the total amount of ground that I have covered. I would have to get out my meter stick. I would have to measure every single meter along this path. And that would be the distance that I covered. So kind of this green line, that is my distance. Meanwhile, if I were to measure my displacement, it would just be this length right here. Just the difference between my starting and ending position. You've probably heard the phrase, it's about the journey, it's not about the destination. Well, when it comes to displacement, it is about the destination. It's only about the destination. The concept of displacement does not care what happened in between the start and end. Those are the only things that it cares about, just the start and just the end. All right. Now, in order to keep talking about displacement, we got to talk about a couple special types of mathematic quantities, because you see, displacement is what's called a vector quantity, and so are velocity and acceleration. They're all vector quantities. So let's talk about what a vector is and how it's different from something called a scalar. Maybe you've seen Despicable Me. In the movie, there's that character Vector, and he keeps on talking about how he has direction and magnitude. And he was actually teaching you about math. In reality, what he was saying is pretty much true. That's kind of how we define a vector, whereas a scalar is just something that has magnitude. Now, in this case, magnitude is kind of the value of the mathematic quantity, right? It is the amount of however much you are talking about. So like 40 meters per second. Let's say I have a car moving at 40 meters per second. 40 is the magnitude, right? That is how much velocity it has. And then the direction would be, towards me, away from me, right? It's important for these terms here for you to know the direction, because a car moving at 40 meters per second away from you is very different than a car moving at 40 meters per second towards you. That's a key bit of information that we need to know about in order to analyze that information. So the direction is really important. But if these are mathematic quantities, how do we denote direction? How do we show the direction of these mathematic quantities? The answer to that is we're going to use positives and negatives. So check it out. When it comes to physics, most of the time we are going to say that to the right and up are positive directions, and to the left and down are negative directions. Now, that is not this inherent fact about the world. It is kind of just a convention that we use in physics to help us all be on the same page for the most part. But in reality, I could take this and totally flip it around. Let's say I wanted to do a problem, and sometimes in certain situations, it would be helpful for me to say that that to the right is negative and to the left is positive. I can do that. There's nothing saying I can't do that. We're not going to unless it actually helps us, though. There's no point in changing it unless there is a reason to do it. So there will come a time in this class where we are going to flip the positive and negative direction, or maybe just change which direction is positive, but we'll only do it to make our lives simpler, okay? Let's look at a couple examples of this, and let's kind of investigate here, how do acceleration and velocity interact with each other? So here I've got a car driving down the highway. It has a velocity vector and an acceleration vector. So it is moving down the road and it is accelerating down the road. Both of those vectors are pointing in the positive direction. And the big question is, do I think this object is speeding up or slowing down? Well, the answer here is my object is speeding up, okay? The object is speeding up. Why? Well, recall that the acceleration of an object is just its change in velocity. So if the change in velocity is happening in the positive direction, it is changing velocity in the positive direction, then it is stretching velocity out in the positive direction, increasing its value in that positive direction, meaning it's going faster, right? It's speeding up. Okay, but what if I were to flip this and say, okay, now acceleration is pointing in the negative direction and velocity is pointing in the positive? Well, this time, acceleration would essentially be stretching it back or shrinking it, pulling it back down to zero, right? Because the negative direction from a large positive number, the negative direction is towards zero. So my velocity will become smaller and smaller. So that means we're slowing down. Okay? Let's flip it again. Say it's going this way. So now I have a negative velocity and negative acceleration. Well, my acceleration is causing the velocity to be stretched in the negative direction, but it's already pointing negative, so it's just going to become a larger number in the negative direction. What does that mean? That means it's speeding up. Okay? And then kind of the final iteration of this is we keep our negative velocity, but now we have a positive acceleration. Are we speeding up or slowing down? Well, acceleration is pulling the velocity vector in the positive direction, but if it's facing the negative direction, the positive direction is towards zero. So it is becoming smaller and smaller and smaller. My object is slowing down. All right, so kind of the big generalization I'm going to make here is that if our velocity vectors are pointing in the same direction, whether it's to the right or to the left, right, positive or negative direction, as long as those vectors are pointing in the same direction, we're speeding up. Then if those vectors are pointing in the opposite direction, we're slowing down, whether that be one to the left, one to the right, or the opposite of that. Okay, so vectors pointing in the opposite direction, we're slowing down. Vectors pointing in the same direction, we're speeding up. All right. Hey, let's talk a little bit about motion graphs now. We can get a lot of information about different motion graphs by just looking at one motion graph. We can get, by just looking at our position versus time graph here, we can get information about both our velocity and our acceleration versus time graph. And let's talk about how we do that. Well, in order to figure out what our velocity graph is based on our position versus time graph, what do? We look at the slope of our position versus time graph, right? So if I were to take a point, like let's say like about halfway through here, and I look at the slope, I calculate the slope, I get a numeric value for the slope. That numeric value will be the same as the y value of the velocity at that same point in time, right? So the slope informs the velocity versus time. The slope of the position versus time graph informs the velocity versus time graph. And we can kind of take another step up the ladder. We can say, how do we get from velocity versus time to acceleration versus time? It's the same way. It's slope again. We look at the slope of our velocity versus time graph. That gives us the y values of the acceleration versus time graph. Okay, but what if we wanted to go down the ladder? Could we look at information from the acceleration versus time graph and learn something about the velocity versus time graph? And the answer is yes. Unfortunately, we're not going to get the whole picture, but we are going to get part of it. So check it out. If we look at the area under the curve of the acceleration versus time graph, so the whole area of the graph between the line itself and the x-axis, we were to calculate that area, that would tell us the change in velocity for a velocity versus time graph. So again, we're missing some details there, but it would at least tell us the distance between the initial and final velocity. So it would essentially tell us that distance right there. It wouldn't tell us the initial velocity. It wouldn't tell us the final velocity. It would just tell us the distance between those two values. So again, not the whole picture, but at least some of it. And that trend continues. If we found the area under the velocity versus time graph, that would tell us the total displacement or change in position of our object. Okay? So it's kind of like a ladder. We can go up the ladder by finding the slope. We can go down the ladder by finding the area. Let's look at an example of this. Let's say I got this velocity versus time graph, and I asked you to find what is the change in position of this object. Well, we're going to have to find the area under this curve. I don't know about you, but I don't know the area of a trapezoid right off the top of my head. So what am I going to do? I'm going to split this into smaller chunks of shapes that I definitely know the area to. I know the area of a triangle, so I can calculate that. I know the area of a rectangle. I can calculate that. And then this one's just a triangle again. So that's going to make my life a lot easier in terms of figuring out the displacement of this object. So check it out. This triangle right here, we have base 10, height 60, so the area will be 300. The rectangle here, base 5, height 60, we're going to have an area of 300. This triangle over here, base 15, height 60, the area will be 450. So now what do? We're just going to add these three numbers together, and we are going to end up with our total answer. It's the area under the graph, as well as the distance that this, or the displacement that this object experienced of 1,050 meters. Again, that is just how far the object has moved. That is not its final position. The object's final position is not 1,050 meters from where it started. It could have started 100 meters away from the origin, and now it's just moved an additional 1,050 meters away. Okay? So kind of an important detail to keep in mind when we're making these calculations. Let's make one last one. Acceleration versus time graph. I want to figure out what is the change in velocity of my object. Okay. Well, we have to find the total area of this graph all the way down to the x-axis, right? Which means that we've got kind of a weirdly shaped object. So again, I'm going to split it up. I'm going to split it like this. So now I've got a rectangle that looks like this, and a triangle that looks like this. That's going to make my life a lot easier. This triangle has a base of 5 and a height of 5, so that's 25 divided by 2 is 12.5. Then our rectangle has a base of 5 and a height of 1, so the total area there will be 5. So we add those two together. 17.5 meters per second is the answer to the question, how much did the velocity of this object change over the course of this time? Okay, that wraps up our notes here. Hope this was helpful.